You think you know what nothing is. Empty space, a vacuum. Remove everything from a room, and what's left is nothing. Simple, obvious. You've understood nothing your whole life, but have you ever actually thought about it? What is nothing? Not philosophically. Physically, what happens when you remove everything? What's left? Most people shrug. Nothing is nothing. It's the absence of stuff. It's what you get when there's no matter, no energy, no light, no anything. It's the default state, the blank canvas, the zero. That answer is completely wrong. Nothing is not nothing. And when you understand what empty space actually is, when you see what's really happening in the places where you think there's nothing at all, it changes everything you thought you knew about reality itself. Let me show you what I mean. Start simple. You have a box, a sealed container. You want to create nothing inside it. How do you do that? First, you pump out all the air. Every molecule of nitrogen, oxygen, carbon dioxide, gone. Now you have a vacuum. Is that nothing? No, there's still light in there. Photons bouncing around. So you make the box perfectly opaque. No light can enter or escape. Is that nothing? No. The walls of the box are warm. They're radiating infrared radiation into the interior. Heat, energy. So you cool the box down, way down. You take it to nearly absolute zero, the coldest possible temperature, minus 273.15 degrees Celsius. As cold as physics allows. Now is it nothing? Still no, because even at absolute zero, even in perfect darkness, even with every atom removed, there's something there. Something you can't pump out, something you can't cool away, something that refuses to leave no matter what you do. The vacuum is not empty. The vacuum is seething. This should bother you. You removed everything. You took out every particle, every photon, every bit of energy you could possibly extract, and something is still there. What is it? Where did it come from? Why can't you get rid of it? Here's where your intuition starts to fail. You think of space as a container, a stage where things happen. Matter exists in space. Energy moves through space. But space itself is just the backdrop. The emptiness between things. The void that separates objects from each other. Wrong. Space is not a container. Space is a thing. And it's not empty. It's full. Full of what? Fields. Quantum fields. They're everywhere. They permeate every point in the universe. You can't escape them. You can't remove them. They are the fabric of reality itself. Think about what a field is. You've heard of magnetic fields, electric fields, gravitational fields. These aren't just mathematical abstractions. They're not just convenient ways to do calculations. They're physical realities that fill all of space. At every point in the universe, right now, there's an electromagnetic field. It might be very weak in some places, very strong in others, but it's never zero. It's never absent. It's always there. And there's not just one field. There's the electron field, the quark field, the Higgs field, dozens of quantum fields, all coexisting, all overlapping, all filling every cubic centimeter of the universe simultaneously. Now here's the part that breaks everything. These fields don't just sit there quietly. They fluctuate, they jiggle. Even in their lowest possible energy state, even when there's nothing to disturb them, they're constantly vibrating, randomly, unpredictably, at every point in space, all the time. Why? Because of quantum mechanics. Because of something called the Heisenberg uncertainty principle, the most important idea in modern physics, the idea that changed everything. You've probably heard of this. You can't know both the position and momentum of a particle exactly at the same time. The more precisely you know one, the less precisely you can know the other. That's the famous version, the one they teach in school. But there's another version, one that matters here. You can't know both the energy of a system and the exact time it has that energy. If you want to know the energy precisely, you need to wait. If you only look for a brief moment, the energy is uncertain. It could be anything. And here's what that means for empty space. If the vacuum had exactly zero energy, we would know its energy precisely. Zero. Exactly zero. Forever. But quantum mechanics says you can't have that. You can't have exactly zero energy for any extended period. The uncertainty principle forbids it. It's not that we lack the instruments to measure it. It's that nature itself doesn't allow it. So what happens instead? The energy fluctuates. It borrows from zero, then pays it back, up and down, constantly, at every point in space. These fluctuations are tiny. They happen over incredibly short time scales, billions of billions of billions of a second. But they're real. They're always happening. Right now, right where you're sitting. The vacuum around you is fluctuating. And those fluctuations create something. Particles. Virtual particles. Wait, particles from nothing? Yes, sort of. The energy fluctuations are large enough, brief enough, that they can create particle-antiparticle pairs. An electron and a positron pop into existence out of nothing. A quark and an antiquark appear from the vacuum. They exist for an unimaginably short time, then they annihilate each other and disappear back into the vacuum. Gone as quickly as they came, borrowed energy returned. This is happening constantly, everywhere. Trillions of times per second in every cubic centimeter of space. Particles appearing and disappearing. Matter and antimatter flickering in and out of existence. The vacuum is boiling with activity. A churning sea of creation and annihilation that never stops. Now you're thinking something. You're thinking these virtual particles aren't real. They're just mathematical tricks, bookkeeping devices, useful for calculations, but not actually there. They don't actually exist because you can't see them or detect them directly. Wrong. Again, we can detect them. We have detected them multiple times, in multiple ways. The effects of virtual particles are measurable. They're real. They affect the physical world in ways we can observe and quantify. Here's the proof. Take two metal plates, flat, uncharged, perfectly smooth. Place them very close together in a vacuum, a few nanometers apart, smaller than a wavelength of visible light. What happens? They attract each other. Think about that. Two neutral plates, no charge, no magnetism, nothing between them except empty space, and they pull toward each other, a force from nowhere, a push from nothing. Why? The answer is virtual particles. The quantum fluctuations between the plates, only certain wavelengths of fluctuation can fit. The gap is too small for longer wavelengths. Outside the plates, all wavelengths are possible. No restrictions. This creates an imbalance. More fluctuations pushing from outside than from between. More pressure on the outer surfaces than the inner ones. The plates get pushed together. This is called the Casimir effect. It was predicted in 1948 by Dutch physicist Hendrik Casimir. It was measured precisely in 1997 by Steve Lamoureux at Los Alamos National Laboratory. The force is tiny but real, about 100,000th of an atmosphere. Barely anything, but definitely something. We can calculate it from quantum field theory and measure it in the laboratory. They match, exactly. Nothing is pushing those plates together, except nothing isn't nothing. Let me make this even more concrete. The magnetic moment of the electron. You remember electrons? Tiny particles with negative charge. They also have a tiny magnetic field, like a little bar magnet. We can measure how strong that magnetic field is. We can measure it very precisely, to more than 10 decimal places. One of the most accurate measurements humans have ever made. We can also calculate it using quantum field theory. We account for all the virtual particles constantly surrounding the electron, interacting with it, affecting its properties. Photons, electron-positron pairs, all the quantum fluctuations that swarm around every electron in existence. The calculation and the measurement agree to 10 decimal places. 0.00115965218.073. Calculated. 0.00115965218.076. Measured. One of the most precise agreements between theory and experiment in all of science. The virtual particles are real. Their effects are measurable. Nothing is something. Here's where it gets worse. If the vacuum has energy, if these fluctuations are real, they should have gravitational effects. Energy curves space-time. That's what Einstein taught us. Mass and energy are the same thing. E equals mc squared. So the energy of the vacuum should curve space. It should affect the expansion of the universe. And it does. We call it dark energy. The universe is expanding, and that expansion is accelerating, getting faster every moment. Something is pushing space apart, something invisible, something that fills all of empty space. The best explanation we have is that it's the energy of the vacuum itself, the cosmological constant. Empty space has a non-zero energy density that makes the universe expand faster and faster. But here's the problem. When we calculate how much energy the vacuum should have based on quantum field theory, we get a number. When we measure how fast the universe is actually expanding, we get another number. These numbers don't match. They don't just disagree a little. They disagree by a factor of 10 to the 120th power. That's 1 followed by 120 zeros. The worst prediction in the history of physics. Not even close. Off by more than the total number of atoms in the observable universe. We know the vacuum has energy. We can measure its effects, but we can't explain why the amount is what it is. This is called the cosmological constant problem. It's been called the most embarrassing problem in physics. We don't have an answer. We don't even have a good guess. The vacuum mocks us. The vacuum is real. Its effects are measurable, and we don't understand it. Now step back and think about what this means. You thought empty space was simple, the absence of things, the default state, nothing, the easy part, the baseline from which everything else is measured. But nothing is the most complicated thing in the universe. Nothing is full of fields. Nothing is fluctuating constantly. Nothing is creating and destroying particles trillions of times per second. Nothing has energy. Nothing curves space-time. Nothing is driving the expansion of the universe. Nothing contains mysteries we haven't solved. You are swimming in nothing right now. The space around you, between the atoms in your body, between the electrons and the nuclei, that space is not empty. It's alive with quantum fluctuations. Virtual particles are appearing and disappearing inside your body constantly. The vacuum is seething right where you sit. You've never been in true emptiness. You never will be. Here is another thing that should disturb you. All the matter you see, all the atoms, all the stuff that makes up planets and stars and galaxies and you, it's really just excitations of these fields. Ripples, disturbances, waves in the quantum sea. An electron is not a thing sitting in space. An electron is a vibration in the electromagnetic field. A photon is a vibration in the electromagnetic field. A quark is a vibration in the quark field. Matter is not separate from the vacuum. Matter is what happens when the vacuum gets disturbed. The particles are the excitations. The vacuum is the ground state. But even the ground state isn't zero. Even the lowest possible energy has fluctuations. You can't turn it off. You can't make it stop. This means the distinction between something and nothing is not as clear as you thought. Nothing is already something. The vacuum is not absence. It's presence. A different kind of presence than the matter you're used to, but presence nonetheless. Think about what you call empty space. The gap between Earth and the moon. The void between galaxies. The darkness between stars. You call it nothing. You call it empty, but it's full of quantum fields, full of fluctuations, full of virtual particles winking in and out of existence, full of the dark energy pushing the universe apart, full of mysteries. There is no nothing, not anywhere, not ever. The vacuum state is the foundation. Everything else is built on top of it. When you remove all the excitations, all the particles, all the radiation, you don't get nothing. You get the vacuum. And the vacuum is something strange, something that refuses to be zero, something that insists on fluctuating even when there's nothing to fluctuate. You wanted nothing to be simple, a blank slate, the easy case, the baseline, But the baseline is the hardest thing to understand. The foundation is the mystery. What we call nothing is the deepest puzzle in physics. Why does the vacuum have the energy it has? Why don't the virtual particles add up to tear space apart? Why is there something rather than nothing when nothing is already something? We measure, we calculate, we observe the effects, but the vacuum keeps its secrets. You thought you understood nothing. You didn't. Nobody does. The simplest thing, the emptiest thing, the most absent thing you can imagine, it turns out to be the most complex, the most active, the most present. Nothing is not nothing. Nothing is everything in disguise. And the harder you look at the emptiness, the more you find that the emptiness is looking back at you, full of things you never expected to see. That's what nothing actually is. Not absence, not emptiness, not the default. The vacuum is the stage, the actors and the play all at once, constantly performing, even when the theater is closed, even when no one is watching, even when you swear there's nothing there. There isn't nothing there. There never was. There never will be. Every time you point to empty space and say there's nothing there, you're wrong. Every time you imagine the void between atoms, the gaps in matter, the darkness between stars as absence, you're missing what's actually happening. The quantum fields are there. The fluctuations are there. The virtual particles are there. The energy is there. The mystery is there. You started by thinking nothing was the simplest concept in physics, the absence of things, the easy baseline. Now you know it's the opposite. Nothing is where all the hardest questions live. Nothing is where physics breaks down. Nothing is where the 120 order of magnitude error lives. Nothing is where the foundations are shakiest. The universe doesn't know how to be empty, and now neither do you.